Okay, light waves. Let's يعني recap quickly. What did we say? What did we talk about in light waves before? Well, light waves, first of all, we need to discuss the reflection, refraction, and dispersion of light waves. Basically, the reflection of light waves, in reflection, we have mirrors. If we talk about the reflection, okay, reflection, we have mirrors. Usually light waves reflect in on reflective surfaces such as the mirrors. If I have an object on this side of the mirror, okay, this is an object X, this is the object X. We want to find the image of this object, the image of the object. Okay, I guess there's a C here. Okay, how can I find the image of this object in the mirror? You tell me the image should be exactly on the أو يعني the distance between the object and the mirror should be equal to the distance between the mirror and the image. For example, if the distance is 20 centimeters, okay, then the distance between the mirror and the image, okay, would be also, this is the image, okay, distance would also be 20 centimeters. But there's a question. There was a very famous question in paper two. He asked you, what was the distance between the object and the image? What was the distance between the object and the image? And distance between the object and the image is 40 centimeters type. How can I draw some arrows or some waves or whatever to find the image? First of all, you need to draw two main lines or two main rays. This first ray, the 20 centimeter distance, it could be considered to be one of the rays. It could be considered to be one of the rays which will reflect and then be extended on the other side to find the image. The second ray, okay, how can I draw another ray with any angle, using any angle from the object to the mirror, using any angle from the object to the mirror, and this is the direction of this wave. And then whenever a wave hits a surface, you need to draw the normal line. First of all, you need to draw the normal line on the surface. طبعا normal line should be 90 degrees. Okay, it should be exactly 90 degrees to the surface. 90 degrees. It is normal 90 degrees. Then you should find the angle of incidence and then draw a reflected wave with the same angle of reflection. So there's a simple law in which the angle of incidence is equal to the angle of reflection. I equals R. How can I find the image? All you do is extend this line. You just extend this line, okay, all the way until it meets the surface, or it meets the other line, until it meets the other line. So first line, this black one, it should meet the red one, and at the point of intersection, this should be the image. In images, in light waves, whenever two rays of light meet, an image is produced. Whenever two rays meet, an image is produced. If two rays do not meet or never intersect, then an image will never be produced. Okay, how can we produce an image يا شباب? By intersecting two rays of light. By intersecting these two rays of light, the image will be produced. يبقى دلوقتي what happened? All I did was draw two lines. I drew two lines. The first line is very simple. Okay, you can actually use it to make sure. Okay, you can use it to make sure that the distance between the object and the mirror is the same as the distance between the mirror and the image, 20 centimeters and 20 centimeters. And then the second ray with any angle. You can draw whatever ray, whatever angle, and then just draw the normal line and measure the angle of incidence, angle of reflection, and extend the line beyond the image. The properties of this image, okay, we have several properties for this image, okay. Let's write them down, okay, some of the properties of this image. Such as images always in the mirror always have the same size, okay, they're always at the same distance, they are always upright, okay. طيب, Mr. They were inverted. No, they weren't inverted. They weren't vertically inverted. They were laterally inverted. Laterally inverted. Okay, so this is what I mean by what does a laterally inverted mean? Laterally inverted image means that the image is simply flipped from left to right. From left to right, the image is inverted. And if I read some words, I wouldn't be able to read them. Why? Because they are inverted from left to right. And last but not least, an image produced in a mirror would be a virtual image. Okay, would be a virtual image. يبقى دلوقتي hmm, we have five properties for any image that is produced in a mirror. Any image that is produced in a mirror. What does a virtual image mean? A virtual image means that it cannot be produced on a screen, cannot be produced on a screen. We cannot save this image. We cannot download this image. We cannot print this image. Okay, it cannot be saved on a screen. Once you look away from the mirror, the image خلاص is vanishes. So this is what a virtual image means. So basically, this is a reflection of reflection of light waves, which are quite easy. Moving on to a more difficult subject, a more difficult part of this lesson is the refraction of light waves. Refraction of light waves, we know that the speed of light waves, okay, the speed of the light waves is 3 times 10 to the power of 8 meters per second in air or vacuum. In air or vacuum. طبعا it should be in vacuum. Technically in air, the speed of light is slightly less than 3 times 10 to the power of 8. But we can consider it to be 3 times 10 to the power of 8. Okay, so why does light move at the speed? Actually, what happens when light moves from air to water or from air to glass? It starts to refract. The question is, why does it refract? Why does it bend? Why does it change its direction? As it's moving from one medium to another, as it's moving from one medium to another, the density of this medium increases. In light, actually, you need to differ. You need to be aware of the difference between a light wave and a mechanical wave. A light wave is an electromagnetic wave. What is an electromagnetic wave? It's a wave that can move. Let me write it down. Okay, it's an electromagnetic wave. What's an electromagnetic wave? It's a wave that can move through vacuum. It can travel through vacuum, so it does not require any medium. It does not require any molecules. Okay, doesn't require a medium. It doesn't require any molecules. As the density of the molecules increases, the speed of the light decreases. It becomes too crowded for the light to move. Too crowded. So the light cannot move as easily as it could have moved in the vacuum. As density increases, the speed decreases. But this is the complete opposite of the mechanical waves, such as the sound waves. Sound waves actually, as you increase the density, the speed increases. Okay, so electromagnetic waves are opposite to the mechanical waves. Mechanical waves, they can move. Oh, they actually require a medium, and as the density of this medium increases, the speed of this medium also increases. Okay, so speed of light 3 times 10 to the power of 8 in air or in vacuum. As it moves to another medium, it refracts, it bends. What is refraction? It's the bending of a wave. Okay, what is refraction? Let me write it down. Okay, it's the bending of waves as they change their mediums. Okay, as they move from one medium to another. Okay, let's start by drawing some diagrams. Okay, for example, we have a boundary. Okay, boundary between um, between the air and the, let's say, water or whatever, water or glass. As the light moves from air to water, as the light is moving from the air to the water. First of all, you need to draw the arrows. You need to draw the arrows. You need to state from which medium to which medium is it moving. It's moving from air to water. Okay, so you need to draw this arrow. Then, when you draw the arrow, you need to state where is the. Oh, you need to draw the normal line. Okay, this is the normal line, 90 degrees, and then you have the angle of incidence. This is the angle of incidence. And then you have some wave fronts. Okay, you have some wave fronts which are incident on the boundary. What are these wave fronts? Okay, these wave fronts should be perpendicular to the direction of the motion. They should be perpendicular to the direction of the motion, meaning that I want to, let's say, draw 5, 3, or 4, or 5, whatever, wave fronts. Okay, so these are some of the wave fronts. They are perpendicular to the motion, to the direction of the motion. These are some of the wave fronts, which are perpendicular to the direction of the wave fronts. To the direction of the motion, the distance between any two wave fronts is the wavelength. Distance between these two wavefronts is the wavelength. Okay, and the wavelength should be constant in one medium. If I'm in one medium, if the wave is still hasn't crossed to the other medium, then the distance, the wavelength should be equal. Okay, it should be equal. As it moves, as it passes to another medium, what happens? It starts to bend. Question is, why does it start to bend? I know it has changed the medium. It has changed the medium. But again, why does it bend? Why does it change its direction? Yeah, I know it has changed the medium, but why does it change the direction? If you think about the wavefront, okay, if you think about the whole length of the wavefront, or let's say the whole width of this wavefront, I'm talking about this whole distance, for example, okay, this whole distance. I know it doesn't really matter, but if you think about it, just the first one, it hasn't yet reached the boundary. The second one also hasn't yet reached the boundary. The third one, fourth one. Moving on to the fifth one, only part of the wave has reached the boundary. So this part will start to bend, will start to change its speed first, and then the remaining part of the wave. Okay, for example, this wave. Okay, some of it has entered the medium already, so some of it will start to slow down before the rest of this wave. For the rest of this wavefront, some part of this wave will start to slow down. So part of it will start to bend first. Okay, part of this wave will start to bend first. Part of this wave will start to bend first. Okay, only part of the wave that only the small part of the wave that has already reached the medium will start to bend. It will start to slow down, and therefore, when it starts to slow down, it will start to bend, and the speed will start to decrease, and whatever. And the angle will decrease as you're moving from air to water. What happens to the angle? What happens to the angle of incidence? Well, the angle of incidence in air was greater than the angle of incidence in water. So the angle of refraction in water. As you move through the water, what happens to the angle? It decreases. What happens to the angle? It decreases. Okay, I can draw it again. Okay, what happens to the angle? It kind of decreases. So this is the wave as it moves, or this is the direction of the wave as it moves. And again, the wave fronts are perpendicular to the wave. The distance between the wave fronts has slightly decreased. The wave length has decreased as you're moving from air to water. What happens? Okay, three things actually happen. Let me write them down. What happens? The wavelength decreases, the speed decreases, and the angle, okay, the angle also decreases. What about the frequency? The frequency is always constant. What about the frequency? The frequency is always a constant. Why? Because the frequency is actually a property of the wave that defines this type of wave. Frequency defines the type of this wave. If you increase or decrease the frequency, you're changing the whole wave. You are changing the whole wave. For example, and we will talk about it later on, inshallah, the electromagnetic waves. We have 7 electromagnetic waves. Each wave is defined, okay, by its frequency and wavelength. So as you change the frequency of the wave, you're talking about a totally different waves. Therefore, if one wave, a light, for example, is moving from air to water, then this frequency of this light will change. It will remain constant, but the wavelength and the speed will differ. the wavelength and the speed will differ. Why? Because we have an equation. Okay, speed equals wavelength times frequency. Frequency is constant, so as you decrease the wavelength, the speed also decreases. They are directly proportional, but the frequency is constant for one. If I am talking about one wave, if I'm talking about one wave, light or infrared or whatever wave is moving from air to water. Okay, this is if the wave is moving from the air to the water, the less dense to the more dense medium, the less dense to the more dense medium. What happens if it goes the other way around? What happens if the light moves from the more dense to the less dense? Let me draw a long boundary. Okay, first of all, the light is moving from the water. We have the water and it's moving to the air. For example, initially the light had an angle of incidence. Okay, this is light as it's moving. And then you have the normal line. You have the normal line. Initially, for example, let's say that the angle of incidence was rather small. Okay, let me actually decrease this angle of incidence. Okay, if the angle of incidence, the initial angle of incidence was 20. Okay, let's say this angle was 20 degrees. As it's moving from water to air, from the more dense to the less dense medium, what happens to the wave? What happens to angle? Angle increases. What happens to angle? Angle keeps on increases. So 20, for example, هنا it will be 40. صح? It will increase. 20 هنا becomes 40. Definitely the wavefronts also increase, or the distance between these wavefronts increases. Okay, the speed increases, everything keeps on increasing. 20 it becomes 40, for example. Okay, what about if the angle increases, it becomes 30? If the angle هنا was 30, then the angle will increase much more. Let's say it becomes 60. Okay, but what happens if the angle becomes okay, let me draw another wave. If the angle was 40, okay, I wanted to draw the normal using the red line. Yeah, this is the normal, and the angle is, let's say, 40. Yalla, quickly. 40. What happens to the refracted wave? For example, it would be 85. Okay, it would be around 85, which has increased so much. It has increased definitely so much. When does it reach 90 degrees? When does the wave start to move along the normal? When does the wave start to move along the normal? If the angle of incidence, if the angle of incidence from the more dense medium, if the angle of incidence from the more dense medium becomes equal to a certain angle, which is the critical angle. The critical angle, okay, it's not, you don't need to memorize any critical angle because it would differ from a medium to a medium. Okay, the critical angle sometimes could be around 42, 45. It could reach up to 50. Okay, so the critical angle is always different if you're changing from one medium to another. Water, I guess the critical the critical angle is around maybe 49 or something. Okay, so if you increase the angle slightly until it reaches 49, what will happen? Okay, this is, let's say, 49. What happens to the wave? It moves along the surface. So it moves along the surface. So, and the angle of refraction is 90 degrees. The angle of refraction is 90 degrees. So this 49 is now the critical angle. What is 49? The critical angle. We can define the critical angle. It's an angle of incidence from the more dense medium at which the light refracts at an angle of 90 degrees and moves along the normal. Critical angle is an angle of incidence from where? From the more dense medium at which what happens? At which the refracted light moves along the medium, along the boundary with an angle of 90 degrees. With an angle of 90 degrees. What happens if I increase the angle of incidence from the more dense medium more than the critical angle? A very important phenomenon, which is the total internal reflection. No light will be able to exit. No light will be able to escape, okay, this medium. If the angle of incidence, let's say, was 60, 70, anything above the critical angle, okay, for this medium, let's say this angle was 60, definitely Okay, definitely this angle is, we need to increase it way more than 50. Okay, let's say it's 60. So at 60 degrees, what happens? Total internal reflection. All of the light is reflected back inside the medium. No light is able to escape the boundary. All of the light is reflected back. This is called total internal reflection. We cannot say it's called reflection only. No, it's called total internal reflection. And actually total internal reflection is quite important. Why? Because we use it in our everyday lives, such as in the cables in okay, we do use it. Okay, we do use it in the fiber cables. Okay. Okay, the optical fiber cables. Optical fiber, what happens in optical fiber cables? Let me draw it quite quickly. Okay, if I have an optical fiber cable, okay, this is an optical fiber cable which carries data from one side to the other. Okay, if this is an optical fiber cable, okay, optical fiber. What happens to the light? The light or the infrared. Okay, actually, it could use light or it could use infrared. Why? Because they can both pass through glass or this transparent material. It's not actually glass, it's some mixture between glass and plastic. Whatever, I don't really care about the actual material. It's optical fiber. What happens to the light? As light enters the optical fiber at angles greater than the critical angle. Okay, the angles must be greater than the critical angle. What happens? Okay, light gets totally internally reflected. Okay, so this is the normal line, and then the light is reflected back with the same angle. Okay, and then again we have another normal line at this point, and the light is reflected back. It could exit at the other side, transferring data. For example, internet throughout the whole world is transferred using optical fibers, using huge fibers which are on the seabeds, okay, and ocean beds, ocean floors, all over the world, transferring data through thousands of miles. But actually, since the speed of light is three times 10 to the power of 8, 300 million meters per second, that's why we don't feel any lag. Okay, it's almost instant to transfer any data from one point to another point in any part of the world, okay, using these optical fibers. Angle must be greater than the critical angle so that the light is totally internally reflected inside the medium. How can I, how can you measure these angles? Oh, not measure. How can you calculate these angles? 20, 40, 30, and 60. I just wrote down any numbers. Are these accurate numbers? No, they're not accurate numbers. How can we find the accurate numbers? How can we find these accurate numbers? Using the refractive index. Using HWeb, the refractive index. What's the refractive index? It's a ratio. It's a ratio of between the speed of light in air to the speed of light in a medium. Okay, refractive index. We have several equations, so let's write them all quickly. Okay, refractive index. You can either say that n, the refractive index n, is equal to the speed of light in air over the speed of light in medium. Okay, speed of light in air over the speed of light in medium. If you have to be honest, the speed of light in air is a constant. He will never ask you to find the speed of light in air, and most likely he will not write down the speed of light in air. It's a constant, and you must memorize it 3 times 10 to the power of 8. If he asks you to find the speed of light in the medium, then simply, okay, we could rearrange the equation in which the speed of light in the medium is equal to the speed of light in air over the n. So, but this is the first equation. The second equation is related to the angles. N equals sine theta A over sine theta M, in which theta A is the angle of the light in the air. It doesn't have to be the incident angle of incidence or the angle of refraction, not necessarily. Okay, and the theta M, which is the theta or the angle of the light in the medium. Okay, again, it doesn't have to be the angle of incidence or the angle of refraction. What matters is that this is the angle of light in the air, theta A, and theta m is the angle of light in the medium. Okay, whether it's refraction or incidence. Okay, so this is if you have both angles. Can he ask me to find the theta A? Can I find the angle of light in air? Yes, I can rearrange the equation. If you simply rearrange the equation, then theta A would be equal to sine inverse, okay, n times sine theta m. Okay, theta A is equal to sine inverse, okay, sine inverse n times sine theta m. Can I find the theta m? Can I find the theta, the angle of light in the medium? Yes, you can. Allah, theta m would be equal to sine inverse sine theta A over n, okay, over the refractive n. This is if you're not good with rearranging the equations. You can just memorize them. If you're not good with the equations, then you can just memorize them if you want to find theta A or theta M. There's one last equation which has to do with the critical angle, in which critical angle, if we go back to the diagram, the critical angle, what happens at the critical angle? What happens at the critical angle? Critical angle is 49. So this is the angle of the light in which medium? Is it in the air or in the water? No, it's in the water. It's in whatever medium, water, glass, whatever. So this is the angle of the light in the medium. What is the angle of the light in the air? What's the angle of light in air? It's 90. At the critical angle. At the critical angle, the angle of the light in the air is 90 degrees. Type. You have the critical angle and you have the angle of the light in the air. Can I rewrite the equation? Yes, you can rewrite the equation. Actually, it's the same equation if you think about it. It is the same equation. N equals sine, okay, theta A over sine theta M. Theta M is the critical angle. Okay, so instead of writing theta M, because it's a critical angle, it's a very important angle, I'll just write down sine C. I'll write down sine C. And instead of writing theta A in the critical angle, the angle of light in air would be 90 degrees. So it's actually sine 90. Sine 90. If you use your calculator to find sine 90, it would be 1. So basically, we're saying that n equals 1 over sine C. 1 over sine C, in which C is the critical angle. In which C is the critical angle. So let me rewrite it again. Okay, n equals 1 over sine C. Why did I say 1 over sine C? Because sine theta A, okay, because sine theta A is sine 90 and sine 90 is 1. So n, okay, this is when you have a critical angle, 1 over sine C. 1 over sine C. If you have the critical angle, you can find the refractive index using this equation type. What if I have the refractive index? Can I find the critical angle? Yes, you can. Rearranging the equation by simply rearranging the equation, C would be equal to sine inverse 1 over n. Sine inverse 1 over n. That's it. Okay, so we have a couple of equations. Yes, I know, not that difficult, not that difficult, but we can use them to calculate some of the calculations we need, like the theta A, theta M, the C, speed, if you want to find the speed. Okay. طيب this was يعني a quick recap of reflection and refraction. Reflection and refraction. Let's solve a couple of questions. Okay, let's solve a couple of questions regarding these topics. Okay, regarding these topics. We can open up our classified questions. Okay, paper 4, part 2. Okay, let me open up paper 4, part 2. Okay, um, page 87. Okay, so we can solve some questions. Let's solve some questions. Paper 4, part 2, page 87. Okay, I guess this was easy, I think. Oh, ماشي. Page 87. This had to do with electromagnetic waves. I know we haven't said them yet, but so we can quickly recap the electromagnetic waves. Okay, yeah, electromagnetic waves and speeds and yeah, refraction, reflection, refractive index. Okay, page 87. A Bluetooth headset uses what type of electromagnetic waves? It uses the radio waves. Bluetooth uses radio waves. What about the thermal imaging? What about the thermal imaging? It uses, yes, infrared. Yes, thank you. It uses infrared. Photography of people's faces. Photography, any pictures, any whatever. It uses what? Uses visible light. How can we see images? Using visible light. What about sterilizing medical equipment? Definitely using the gamma rays. Gamma rays. State the speed of electromagnetic waves in vacuum. 3 times 10 uh, to the power of 8 meters per second. Speed of light in vacuum or in air. A Bluetooth headset can be used to listen to music. The headset uses frequency in the range of 2.4 to 2.48 gigahertz. Gigahertz. Calculate the wavelength when the frequency is in the middle of the frequency range. What's the middle? Between 2.40 and 2.48, which is 2.44 gigahertz. 2.44 gigahertz. طيب. This is the frequency. What is gigahertz? Giga means times 10 to the power of 9. Giga means times 10 to the power of 9. Can I find the wavelength? Yes. Speed equals, speed equals what? Speed equals wavelength times frequency. Speed equals wavelength times frequency. Can I find the wavelength? Yes, it is speed over frequency. Again, the speed of light in air is 3 times 10 to the power of 8 over frequency, which is 2.44 times 10 to the power of 9. Okay? 2.44 times 10 to the power of 9. It would be around 0.12. 0.12 meters. صح? 0.12. Okay, this is quite an easy question. Okay. Um, Suggest why a Bluetooth headset only works well over short distances. A Bluetooth headset only definitely works only over short distances. Why? Because radio waves, Bluetooth, to be specific, the Bluetooth, the type of waves which are used by the Bluetooth, which are the radio waves, get weakened. Okay, they lose some of their strength. They lose some of their strength when they pass through too many walls. When they pass through one wall, it could be weaker. Two walls, most probably it wouldn't work at all. So they lose the signal. They get weaker as they pass through walls. Okay, they lose. Okay, they lose power or they get weaker. Okay, let me write it down. They get weaker as they pass through walls. Get weaker as they pass through walls. Okay. ماشي. Moving on to the previous question. ماشي. 5.1 shows a road junction moving car. Driver X is at position X. The driver moves around the corner. Label a point Y on the road where the truck driver first sees the car. Where the truck driver first sees the car. This is a nice question. As the car is moving through the corner, when could the truck driver first see the car? Um, Definitely it should be somewhere. يعني as the car is moving, صح, as the car is moving, it would be somewhere at this point. Somewhere at this point, as the car is moving through the curve, the truck driver could see him at this point. صح? He could see him when the car is at this point. If they're both moving at very high speeds, they would collide. Why? Because they're too close and they wouldn't have any time to brake. صح? So this is point Y. Definitely don't you don't need to draw this arrow. To avoid accidents, what did they do? They put a mirror. صح? How does this mirror allow the driver of the truck to see the car when it is at the position shown? The mirror would allow for more light to reflect at wider angles. More light to reflect at wider angles. So we can draw a ray. Okay, we can draw a wave moving from the car that could be reflected towards the driver, towards the truck driver. Okay, how can we draw it? Well, it could be with some angle. Okay, for example, يعني around this angle. Okay, again, you're drawing with a ruler. You are drawing with a ruler, and at this point, you should have normal line. Okay, and this normal line would reflect the ray with an angle of incidence equal to the angle of reflection. Angle of incidence equal to the angle of reflection. Again, you're drawing using a ruler, and you're trying to be as accurate as possible. Okay, try to be as accurate as possible. If the angle is 15 degrees, if you draw it 14 degrees, it's okay. It doesn't really matter that much. But again, try to be as accurate as possible. Don't use your hands only. You must use a ruler and a protractor to measure the angle of incidence and the angle of reflection. Okay. This is the car, and now the truck driver can see the car more easily. Okay, let's move on to more questions. State what is meant by total internal reflection. Well, this is a nice question. What is meant by total internal reflection? Well, total internal reflection happens when the light is moving from the more dense medium to the less dense medium at an angle greater than the critical angle at which none of the light is refracted, or none of the light is none of the light escapes from the surface. Light, okay, when light travels from the more dense medium, yeah, dense medium, to the less dense medium, yeah, less dense medium at an angle of incidence greater, okay, than the critical angle at which no light refracts. No light refracts. All of the light, all of the light is reflected. All of the light is reflected back. Okay, back into the medium. Total internal reflection. Okay, the ray of light strikes the surface of the liquid at an angle x. At an angle x. The refractive index of liquid is 1.5. Calculate the largest value for x for which total internal reflection can occur. The largest value of x for which the total internal reflection can occur. This is a really nice question. Honestly, it's a really nice question. First of all, you have to understand that x is not an angle of incidence. So you need to understand that x is not an angle of incidence. Okay, x is the complementary angle. Okay, it is the complementary angle. This is the normal line. Where is the angle of incidence? This is the angle of incidence. So how can I find x? It's actually 90 minus I. X is what is 90 minus I. This is a complementary angle. It's not the angle of incidence. So how can I find the angle of incidence? How can you find the angle of incidence, the greatest angle of incidence? Well, the greatest angle of incidence, if you have the refractive index, what can I do with only the refractive index? We had a couple of equations. We had a couple of equations finding the refractive index. To find the speed, I don't care about the speed now. So, what about the angle of refraction and angle of incidence, or angle of light in air and the angle of light in medium? I don't have the angle of light in medium, and I do not have the angle of light in the air. But I have one very important equation, which was the critical angle equation. The critical angle. Can I find the critical angle? Yes. N equals 1 over sine C, and therefore C equals huh, sine inverse 1 over 1.5. C equals sine inverse. This is not sine, this is sine inverse. 1 over 1.5, in which C would be equal to 42. This is the critical angle. Is this the final answer? No, it's not the final answer. 42 is the critical angle, which is I. Which is I. I is 42. Therefore, X would be equal to 90 minus 42. X would be equal to 90 minus 42, which is 48 degrees. Okay, 48 degrees. This is a really, really nice question. Okay, because X is not the angle of incidence. X is not the angle of incidence. It's the complementary angle. Speed of light in air is 3 times 10 to the power of 8, which is a redundant statement because you have to memorize this number. You have to memorize this speed. Calculate the speed of light in the liquid. Okay, I have one equation, N equals VA over VM. And therefore, VM, okay, speed of light in the medium would be equal to VA over N. 3 times 10 to the power of 8 over 1.5 over 1.5, which is around 2 times 10 to the power of 8 meters per second. 2 times 10 to the power of 8 meters per second. يبقى x would be 48 and the speed would be around 2 times 10 to the power of, it's not around, it is 2 times 10 to the power of 8 meters per second. Okay, it's a really, really nice question. I like this question. Okay. Yeah, I need to solve one more question at least. But I needed the question that had to do with actual drawings. Monochromatic light, we will discuss it further on, but monochromatic light is light with one frequency. Again, this is dispersion. Okay. هنا this is drawing. Okay. Yeah, this is page what? Page 81. Okay, page 81. On figure 7.1, accurately draw the path of the ray within the prism from face AB to face AC. You will need to make measurements from figure 7.1 and carry out a calculation. Okay, figure 7.1 shows a ray of light approaching. The refractive index is 1.5. The refractive index is 1.5. Can I find out, can I make some calculations? Yes, you can make some calculations. First of all, you need to find the angle of incidence. How can I find the angle of incidence? By drawing the normal line. So first of all, you need to draw the normal line. Second of all, can you find the angle of incidence? You need to be very accurate while drawing this question, okay? Because he said accurately draw. Okay, the question he said accurately draw. So where's the angle of incidence? This is the angle of incidence. The angle of incidence, if you use your protractor, it would be around about 60 degrees. I is now what? 60 degrees. I is 60. As the light refracts while entering from side AB, what will happen to the light? It will refract. Definitely the angle of refraction would be less by how much, using the equation N equals sine theta A over sine theta M. Can I find theta M? Yes, we can find theta M, in which theta M would be equal to sine inverse sine theta A over N. Sine inverse sine 60 over 1.5. Sine inverse sine 60 over 1.5. This would give you an angle of 35, around 35. Okay, can I draw the refracted ray at an angle of 35? Yes, you can draw an angle which would move somewhat like this. Okay, probably it would refract even more. Okay, definitely you are using your protractor. Okay, use your protractor. I guess it would refract a little more, somewhat like this. So this is the angle of refraction, which should be equal to 35 degrees. 35 degrees. Yes. This is a phone marker. This is a phone marker. It's a really nice question. Okay. You have to be able, make sure that you do know how to draw angle of incidence, angle of refraction, to take accurate measurements, to calculate the theta m, angle of incidence and medium. Okay. You need to make sure that you can do these measurements. Okay. Theta m 35 degrees, we drew the line until it reached side AB, or face AB. Determine the angle of incidence of this ray when it strikes face AC. When it strikes face AC, يعني when it strikes face AC, يعني we need to take a measurement, take a reading of the angle at this point. At this point. Yeah, at this point. I need to take a measurement. Okay. You can use, if you use math, it would be a bit difficult. Actually, if you measure this angle, this very small angle, okay, if you measure this very small angle, it would be around 10 degrees. Okay, it would be 10 degrees. This very small angle. This is the angle of incidence as it reaches face AC. Okay, 10 degrees. Again, you need to draw the normal line accurately. It's a very difficult question because of the drawing, not because of anything else. Okay, if you're good at drawing, then this question will be a piece of cake for you. If you're not good at drawing, then you need to be good at drawing. Okay, you need to make sure that you can draw these lines and these angles and take measurements and do whatever is needed to solve these questions. Okay, this is the angle which would be 10 degrees. Without further measurement or calculation, sketch on figure 7.1 the approximate path of the ray after passing through face AC. After it passes through face AC, what will happen? This is the normal line. Will it go closer or further away from normal line? It definitely will go further away from the normal. Without any calculations, we can just draw an angle moving further away from the normal line. Okay, this is the refracted ray as it exits, okay, as it leaves side AC. Okay, yeah, okay, good. Figure 7.2 shows a ray of light traveling within an optical fiber. Complete the path of the ray to the left hand end of the fiber. As it moves to the left hand end, what will happen? That the total internal reflection. Okay, total internal reflection. Um, Can I draw it? Yes, you can draw it. Definitely, you need to take some measurements. This is the normal line as the ray moves, okay, with a huge angle. With a huge angle. It probably will meet this end of the optical fiber only at this very far end, okay? And then it will reflect again. It will reflect again, okay, moving outside, okay, moving outside of the optical fiber. So it reflects again back outside. This is the total internal reflection. In the process taking place at X, total internal reflection. Total reflection. Again, you have to be very accurate while drawing these drawings, please. Okay, drawing lines in the light waves needs to, yeah, you need to have a very very high level of accuracy while taking the measurements while drawing these lines. Please do not waste any marks. Okay, please don't do that. Yeah, this is the total internal reflection. Okay, yeah. Moving on, let's go on. We need to finish up um, what we need to do today, which is the dispersion, electromagnetic waves, and last but not least, the lenses. Let me very quickly go through dispersion and electromagnetic waves. Okay, very quickly. I don't want to waste too much time in the electromagnetic waves. Okay, electromagnetic waves. What are these electromagnetic waves? We have Rami. Okay, Rami. looks great. Rami looks great. In which R is radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. As we are moving in this direction, what happens to the wave? Uh, what happens to wavelength? The wavelength decreases and the frequency increases. Definitely, if you're moving the other way around, the wavelength will increase and the frequency will decrease. The radio waves have the highest wavelengths and the smallest frequencies. Okay, the highest wavelength and the smallest frequency, while the gamma rays, okay, have the shortest wavelength and the highest frequencies. They all have the same speed, 3 times 10 to the power of 8, and they all have some different properties. Okay, we can discuss the properties very quickly. The radio waves, as we said, they are used in Bluetooth headsets. They are used in communications without any satellites. Communications without satellites. Microwaves are used in the microwave ovens, definitely, and they are used in communications with satellites, such as in mobile phones and in satellite television. Satellite television uses microwaves. Satellite television uses microwaves. Microwaves could be harmful because they could cause some heating effect. They could cause heating to internal organs or whatever. Okay, they could be harmful. Too much microwaves. Too much microwaves. Any excessive use of any of these waves would be definitely harmful. Infrared rays are used in what? They are used in the intruder alarms. They are used in the remote controls. Okay, basically to heat up the sun, heats up the earth by infrared radiation. Infrared radiation. Definitely the visible light, okay, is used in photography and in seeing and whatever. Ultraviolet waves, ultraviolet radiation, not waves, ultraviolet radiation is used in what, Ishweb? It's used in several things, such as ultraviolet radiation are used in what? They are used in detecting fake banknotes. They are used in medical uses such as the dentist and whatnot. They are used in tanning. Okay, tanning. Definitely, any excessive use of ultraviolet radiation, especially when we increase the frequencies. When we increase the frequencies in ultraviolet radiation, X-rays and gamma rays, these waves are more, okay, they are definitely more harmful than the radio waves, microwaves, and infrared. Why? Because the frequency has increased, and therefore the energy inside these waves has also increased. The energy has to do with the frequency of the wave. So if the frequency is too high, then the energy the kinetic energy of this wave would be high, and it could be harmful to humans and to life. Ultraviolet radiations, too much or excessive ultraviolet radiation could cause radiation sickness. The same goes for the X-rays, which are used in the security scans, okay, security checks, and the bone scans, checking for any broken bones. And last but not least, the gamma rays are used for what? They are used for medical, such as the sterilizing medical equipment. They can be used for curing cancer. But on the other hand, too much gamma rays could cause cancer. I mean, gamma rays could be used to cure cancer, but too much or the excessive use of gamma rays could cause cancer. Um, so we need to be very precautious while using gamma rays. What are some of the main precautions while using gamma rays or X-rays? Definitely decrease the time of exposure. We need to increase the distance between us and the source, and we need to use some protective shield or some protective barrier between us and the source. Okay, so these are some of the precautions while using gamma rays or X-rays. This is the electromagnetic waves. Very quickly, again, moving on to dispersion of light. What happens during the dispersion of light? As the dispersion, okay, of light. What happens as white light goes through a prism? It's usually a triangular prism. As white light goes through a triangular prism, what happens to white light? It gets dispersed. It refracts and disperses. Both. It refracts and disperses. So as it refracts, as this is the white light. What happens to white light? It refracts and disperses. into the seven colors we know of. Okay, into the seven different colors we know of. Definitely, it needs refract a bit. Okay, okay, seven colors which are Roy, okay, Gibiv. Roy Gibiv. Red, orange, yellow, green, blue, indigo, and violet, in which red has the highest wavelength, okay, the highest wavelength and the least frequency, longest wavelength. Violet has the shortest, the shortest wavelength and the highest frequency. The shortest wavelength and the highest frequency. When we say that red, okay, is the highest or the longest wavelength, this means that it's the least refracted. This is the least refracted. And violet is the most refracted. Okay, so refraction has to do with the frequency of this light color. As you increase the frequency, the refraction will increase. As you increase the frequency, the refraction will increase. These are the seven visible lights, seven colors of the visible light. We cannot see infrared. What is infra? What does infra mean? It means that it has a frequency less than the red light. Frequency less than the. That's why you cannot see it. Infrared. What about ultraviolet radiation? A frequency above the violet color. We cannot see ultraviolet radiation. Why? Because it has a frequency which is higher than the violet color. Roy Gbiv. We have seven colors. These are the visible, okay, colors. Spectrum of visible light, as we say. The spectrum of visible light. Type. What does a monochromatic light mean? Monochromatic is a light with one frequency. Okay, one frequency, one color, one wavelength. Monochromatic. Okay, chromatic means that it is a light with one frequency, one color, and one frequency. Mono means one. Chromatic color. Okay, one frequency. Basically, in physics, we care about the frequency because the frequency is what defines this light. The frequency is what defines this light. And we will discuss this later on in the space physics. Why do I care about these colors? Again, we'll talk about red shifting and whatnot. But for now, one frequency, one wavelength. Okay, okay, one wavelength and one color. One color. Okay. Red has a specific wavelength, blue has a specific wavelength, violet has a specific wavelength, and they all have very specific frequencies. Okay, that's as goes for electromagnetic waves, dispersion, and monochromatic. Also, we need to talk about lenses. We need to talk about lenses. Lenses are very, very important. Yes, we have two different types of lenses. We have convex lenses and we have concave lenses. Okay, lenses. Convex and concave. Let me talk about convex lenses very quickly. If I have a convex lens, okay, this is a convex lens. Okay, with the center line in the middle, okay, and then another line which has it, which is called the principal axis. This is the principal axis, okay, moving through the center of the lens, and then we have 2 points on either side of the lens, which are the principal focuses. Okay, principal focus and principal focus, and the distance between the principal focus and the lens is called the distance between the principal focus and the lens is called the focal length. It's the same on either side. It is the same on either side. This is the focal length, the principal focus, and whatever. What happens during the lenses? How can I produce an image? How are images produced by these lenses, by these convex lenses? As light travels through the lens, lens is it's a different medium. So it could be made of a mixture of plastic and glass or whatever, but it's made of a different medium, a more dense medium. So as the light travels from air to this medium, it refracts. But due to the curvature, due to the curvature of this lens, of this convex lens. It will bend with a certain way. Okay, it bends at a certain way. Bends. Okay, it has a curvature, so it bends, and all of the light will bend and will be focused at a certain point. So all of the light which was moving at a parallel, okay, which was initially parallel, will be focused, will be bent, will be refracted, and will pass through one single point, which is the focal point or the principal focus. And what do I mean? What do I mean? Let me remove this, okay, and start drawing. If I had light which was initially parallel, this light will be focused, okay, it will pass through the focal length. Okay, but this light was initially parallel. What happens? It passes through the focal length. So basically, any light which was initially parallel, which was initially parallel, what happens to this light? It moves through the focal point. Okay, it bends and passes through the focal point. Yeah, this initial parallel light bends and moves through the focal point. خلاص. Yeah, this is the first type of light. Yeah, we have parallel light, parallel rays, parallel rays. What do these parallel rays do? They bend and pass through the focal point or the principal focus. Can the process be inverted? What do I mean by inverting the process? Okay, if the light was initially moving through the focal point, if the light was initially moving through the principal focus, let me use a different color, okay, the green one. If the light was initially moving through the principal focus, what will happen? It will bend and move in a parallel manner, okay? If it was initially moving through the principal focus, it will bend and move through the, move in a parallel way. يبقى if the light was initially moving parallel, it would bend and pass through the focal point. If it was initially passing through the focal point, it will bend and move in a parallel. Okay, so this is a focal, okay, point, and then it will move parallel. Okay, parallel. Last but not least, the most important one, the easiest one actually, okay, the easiest line to draw is the one passing through the center point. This line passing through the center point is not refracted, it's not affected by any way. Okay, if it passes through the center point, it's unaffected and moves, okay, in a straight line. Okay, this is the easiest diagram to draw, the easiest line to draw, as it's passing through the center. As it's passing through the center, it will not be affected. So it will not be affected. Okay, this is the parallel. These are the three lines which we draw. How can we produce images? We produce images when two of these lines intersect. When two of these lines intersect, and therefore an image is produced. The image produced depends on the distance between the image and the lens. Between the image and the lens. If the image distance is huge, then we would have a certain type of image. If the distance decreases, then we could have different types of images. Let me open up a really interesting um, really interesting simulation. Okay, I'll open up a really interesting simulation دلوقتي to show you how these how the light how the image is produced, how the image is produced using these lenses. Okay, هنا we have the, let me open it up now. Okay, convex lens. Okay, convex lens, where are the convex lens? Convex and concave lenses. Yeah. Let me share the screen. Okay. So now we have the object. Okay. I guess you can all see this simulation. We all have the object, which is at a distance of 10 centimeters or whatever. Okay, it's far away from the lens. And the focal length is what? The focal length is 4 centimeters. The focal length is 4 centimeters. Now, the object is at a distance greater than double the focal length. Greater than double the focal length. It's at a distance of 10. Double the focal length is 2f, which is 8. So when it is at a greater distance, at a distance greater than 2f, when the distance is greater than 2f, what happens to the image? What happens to the image? It's inverted and it's real, but it's also diminished. The image is diminished. Image is diminished when the object is at a distance greater than 2f. What happens if the object gets closer at exactly 2f? If the object is at exactly 2f, what happens to the image? Image is inverted and real, but the size of the image is the same. So if the distance, okay, if the distance is equal to 2f, what happens to image? Image is the same, okay, same size. Yeah, same size. When the distance between the object and the lens is exactly 2f, is exactly 2f. What happens if the object gets closer than 2f? If the object gets closer than 2f, between 2f, okay, look, between 2f, this is 2f and f. If the object gets closer between 2f and f, what happens to the image? The image gets larger. Okay, so if the distance is less than 2f, let me okay, if the distance, okay, is less than 2f but greater than f, what happens to image? It becomes larger. It's real, inverted, and larger, or enlarged, or whatever. Okay, real, inverted, and enlarged. What happens about when the object is exactly on the principal focus? If it's exactly on the principal focus, I want to exactly place it on the principal focus. Okay, it's quite difficult to actually place it exactly on the principal focus. Okay, okay. Let's assume that it's exactly on the principal focus. For some reason, it does not want to fit exactly on the principal focus. But if it's exactly on the principal focus, okay, if it is exactly on the principal focus, here it is, alhamdulillah. If it's exactly on the principal focus, what happens? No image is produced. So if the distance is exactly equal to f, okay, if the object is exactly on the focal length, on the focal point, on the principal focus, then no image is produced. No image is produced. Okay? If we decrease the distance even more, if the distance is now less than 4, distance is 3 or 2 or whatever, the image appears again. The image appears again on the other side. The image appears again on the same side as the object. On the same side as the object. When the distance is less than f, then the image is no longer real or inverted. The image no longer becomes real or inverted. Actually, the image becomes virtual, a virtual image. What is a virtual image? Okay, what is a virtual image? It's an image that cannot be produced on a screen. It's an image that cannot be produced on screen. It's an image that cannot be produced on screen. Please, you need to memorize this. Okay, it becomes an upright image. It's no longer inverted. Okay, it's an upright image, no longer inverted. And last but not least, it is always larger. It's always larger. It's always larger. But again, let me repeat the experiment. If we have an object very far away, okay, as the distance increases, what happens to image? It gets smaller. As the distance decreases, what happens to image? It gets larger. At 2f exactly, it's the same size. As distance decreases even more, as distance decreases even more, what happens to image? It keeps on getting larger until at the focal point. At the focal point, exactly at the principal focus, no image appears. What happens if we decrease the image? If we decrease the distance even more, the image appears, but it's virtual, upright, and larger. And actually, to be honest, when the distance is now less than than the principal focus, when the distance is less than the focal length, as the object gets even closer to the lens, the image gets smaller, okay? As the object gets closer to the lens, what happens to the image? It keeps on getting smaller. As the object gets closer, what happens to the image? It keeps on getting smaller, okay? So this is the only difference. And I know as the image gets closer to the lens, as the object gets closer to the lens, the image increases out, the image gets larger. But when it crosses the focal point, it's always larger. The image is always larger after it passes the focal point. The image is always larger. But for example, if the object was at 3, it would have a huge image. If the object was at 2, we would have a much smaller image. Actually, the uh, length of the image or the size of the image decreases further on as it passes through, as it gets closer to the lens. Okay? Okay, good. ماشي. Sorry. I'm really sorry. Let me go back to, And then convex lens. There is another, there is a totally different type of lens, which is called the concave lens. The concave lens. Convex lenses, what do? They converge the light. Okay, these are the convex, okay, lens, or we sometimes call them the converging, okay, converging lenses. What does a converging lens mean? It means that it bends light and it focuses the light into a certain point. Okay, into one point. It bends, it gets light closer to one point. Concave lenses are different, are totally different. They are called diverging lens. Diverging lens. In which in which the light is actually moved further away. Moved further away. What do I mean? What do I mean? This is a converging lens. This is a concave lens. Concave lens would be drawn something like this. Okay, this is, يعني, I can assume that this is an accurate representation. Definitely, this is not an accurate representation. Okay, of a diverging lens. Again, we have the principal axis moving through the center. Okay, this is the principal axis of the lens moving through the center of this lens. Okay, and we can split up the lens into half كده, this way. Okay, um, we have a focal point. بس we have two focal points. Yes, we do have two focal points. Our focal principal focuses on either side. Yes, we do have them. What happens to the light? If the light is moving parallel to the lens, it doesn't go through the focal point. No, it actually moves away from the lens. If the light was moving parallel, what happens to the light? It actually moves it moves away from the lens. This is what we call diverging. Diverging meaning that they move away. They move away from the lens. Diverging means that they move away. Okay, they move away. Technically, okay, if we are drawing a very accurate representation of this of this concave lens, these rays, these diverged rays, could be extended until they reach this focal point on the other side. They could be extended until they reach this focal point on the other side. So if I extend this line, okay, it will reach the focal point. Okay, if I extend this line, it will also reach the focal point. This is the diverging lens. Diverging lenses are used in optical lens. Okay, when uh, okay, we there's a difference, and we do use them. Okay, I'll show you the experiment now. I will show you the experiment now, because sometimes we have short-sightedness, we have long-sightedness. Okay, to see the difference between these two lenses. Okay, we need to see how can I fix short-sightedness, or how can I fix long-sightedness, and I don't know. No, let me show you. Okay, let me show you. Now we have convex lens. These are concave lens and these are convex lens. How can we use them? Okay, how can we use them? Let me open up. Um, let's open up again the classified questions. Okay, open up your classified questions onto page onto page 142. Okay, 142 is the last question in 142. طيب دلوقتي we have driver. He is wearing spectacles to correct long-sightedness. What is long-sightedness? And I don't know what's long-sightedness. Long-sightedness means that the rays, when they enter through your eyes or whatever, okay, they do not meet at the retina. To produce a sharp image, okay, to produce a sharp image, the rays must meet on the retina. The rays, the concave, the bent rays, the refracted rays must meet where? Must meet on the retina. How can these rays meet on the retina? If you have long-sightedness and you need to correct this long-sightedness, how can I correct it? Using one of the two lenses. It's either using a convex lens or a concave lens. It's either using a convex or the concave lens. دلوقتي the rays are moving too far away. يعني actually, if you extend these rays, okay, if we extend these rays, they will meet after the retina. I need to I need to shorten the distance. I need to decrease. You need to what? You need to decrease the focal length. Kind of. You need to decrease this length. How can you shorten this distance? Would it be by using a diverging lens or by using a converging lens? Would it be by using a concave lens or by a convex lens? It's using a convex lens, okay, using a converging lens. Why do I use a converging lens? The eye is already a converging lens. Yes, it is a converging lens. Should I use another converging lens? Yes, you should use another converging lens in which it will bend the light even further. Okay, it will bend the light even more, and therefore the light rays will meet on the retina. How can I draw it? How can you draw it? Let's zoom in a lot more. Okay, I need to zoom in and try to draw يعني ايه a bit more accurately. I will use a convex lens. Okay, this is a convex lens. Okay, this is the spectacles, the convex lens, which are used. Okay, your glasses. What happens? Yeah, the light is moving through the lens. As they move through the spectacles, as they move through the glasses, what happens? They bend. They bend a little. Okay, as the light is moving through the spectacles, what happens? They bend a little. As they bend a little, then they move through the another, okay, through your eyes, what happens? They bend even more and they can meet on the retina. Okay, they bend even more and they meet on the retina. Definitely you can draw this third line which moves straight. Okay, okay, this line is moving along. Okay, it's moving along the principal axis, so it doesn't bend. Okay, it does not bend. This line is moving along the it's moving this way. Okay, it will also meet them at the retina. When the rays meet on the retina exactly, when they meet exactly on the retina, a sharp image is produced. A sharp image is produced. But now I drew the three lines, they met on the retina, and now we have a sharp image. We have a sharp image which is produced. Okay, okay, so using long-sightedness, if I have long-sightedness, I would use a convex, okay, a convex lens. The other one is the short-sightedness, okay. If I had short-sightedness, I would use concave lens, okay, concave lens. Why? Because I need to increase the distance. Need to increase the distance for the light to meet exactly on the retina. Okay, need the light to meet exactly on the retina. Okay, this was a quick drawing. Let's move on. We have a lens. Okay, a page of printed text is placed 18 centimeters from a converging lens on a focal length of 35 centimeters. Printed text is at a length of 35 centimeters. Converging lens, focal length is at 35 centimeters. Okay, 6.1, this is the diagram. Two focuses, we have both of them. A length of 1 centimeter of the diagram represents an actual length of 5 centimeters. 1 centimeter, which is what? Which is these 5 squares. And these 5 small squares represent one represent actually 5 centimeters in real life. By drawing on figure 6.1, locate the image produced by the lens and label it I. I need to find the image of this page. Where this page is this bold line, and we need to find the image. How can we draw the lines? We need to draw simply 2 or 3 lines. You need to draw 2 or 3 lines. First line is what is the line which was moving in a parallel manner, صح? until it reaches until it reaches the center of the lens. And then as it reaches the center of lens, what happens? It bends, it refracts, and passes through the focal point. The second line, it could move through the center of the lens. Okay, it will pass through the center of the lens. Okay, and move directly. Okay, it will not refract. And these 2 lines will not meet. They won't meet on the right hand side. Why? Because the distance between the page and the lens is less than the focal length. And if you have a distance which is less than the focal length, what happens? A virtual image is produced. This image will always appear on the same side as the object. To appear on the same side. How can we draw this image? Extend both lines. I will extend this blue line. This blue line. I will extend it. Okay. I'm extending this line. What about the other line? I will extend this line, the one that has bent, the one that has refracted. I will extend this line. Okay. Definitely you're drawing using a ruler. Okay. This goes without saying. Okay. As they both meet, okay, they will meet somewhere at this point. Okay. They met at this point. Can I draw the page? Yes, I can draw the page. Okay. The image of the page will be somewhat like this. Okay. And you can draw it also extending the below the axis, which will extend almost the same distance below. Okay, so this is the image I. This is the image I of this page. صح? This is the image I of this page. Okay, okay, good. Hmm. I hope you can all draw it. Please, if you don't know how to draw it, يعني just يعني try again. Okay, because all you do is draw 2 or 3 lines. That's all you need to do. Drawing 2 or 3 lines. Hmm. Using figure 6.1, determine the actual distance of image I from the lens. Using the figure, determine the actual distance from the lens. Um, I know my drawing isn't very accurate. My drawing isn't very accurate. How can you draw a very accurate drawing? You need to draw it using your ruler and your pencil and whatever. The actual image should appear. The actual image should appear um, somewhere here, I guess, around. Okay, this should be the actual image. Okay, this should be the actual image. It should be around somewhere here because I'm not drawing using any tools. I'm just using my hand. Okay, so when you draw using your tools, it will be after. Okay, it will be after the focal length. It will be slightly after the focal length. So the distance will be slightly greater than 35. Now, he said that the focal length is 35. Distance should be slightly greater. It should be around 36 centimeters. Should be around 36, okay, centimeters. If you actually count the squares from the center all the way to the focal length, it would be 35, and another one would be around 36 centimeters. Okay, so this is the focal length. Um, Converging lenses are used as magnifying lenses or magnifying glasses. State whether the image produced when a lens is used as a magnifying glass is real or virtual and explain why. As a magnifying glass, are these images real or virtual? طبعا we would say that they are virtual images. Okay, why are they virtual images? Because they cannot be produced on. Okay, they cannot be produced on a screen. صح, produced on a screen. This is a virtual image. It cannot be produced on screen. This is the definition of a virtual image. Cannot be projected on a screen. So just how someone who is long-sighted may benefit from using a converging lens. Long-sightedness. We just solved the question using the long-sightedness. How can he benefit using a converging lens? This converging lens, what will it do? Okay, what will it do to the focal length? Mm. It will decrease the focal length. What will it do to the focal length? It will decrease the focal length. As it decreases the focal length, the image will be produced on the retina. When the image, okay, when the lines, when the rays meet on the retina, a sharp image is produced. Okay, so as they decrease, okay, the converging lenses, what do? They decrease. Okay, they decrease the focal length, and then the image, okay, is produced. The rays meet on the retina. Meet on the retina mm, to produce a sharp image. A sharp image. Rays, they meet on the retina to produce a sharp image. Okay. طيب. This is يلا some lenses. ماشي. Dispersion. We have light which was moving through a prism. A ray of blue light is incident on the prism on the same path of the green light. So this, okay, this was green light. This is a green light passing through the prism. Draw the path of the blue light through and out of the prism. Let's write them down. روي جبف. روي جبف. صح. روي جبف. Blue has a shorter wavelength. So technically it would refract more. Blue should refract more. Refract more. If we had a normal shaped prism, it would be below the green light. But since this image, or since this prism is inverted, it would technically be above the green light. So if this is the green light, the blue light would be above it, slightly above it. Okay, and as it goes out of the prism, it would also be slightly above the green light. So this is the blue light, which is slightly above the green light. Okay, I hope it's clear. Again, we have an object which has distance less than the focal length. This image will be virtual, upright, and enlarged. Okay, measure the distance I, y along the principal axis. Can I measure the distance I, y? Yes, you can measure. When I draw the image, you will be able to measure the distance from I all the way to the center of the lens. Okay, again, why the image is virtual? Because it cannot be produced on a screen. It cannot be produced on a screen. Also, you can say that it's on the other side of the screen, and on the other side of the object. It's on the other side of the. I'm sorry. If it's virtual, because it's on the same side as the object. If it's virtual, because it's on the same side as the object. Right. Um, I wanted to solve one more question. Let's solve this question quite quickly. Okay, electromagnetic waves. State the part of the electromagnetic spectrum that transfers thermal energy. Thermal energy is using the infrared, صح? Radiation. Infrared radiation. It has to do with the thermal energy. طيب. One way in which visible light and radiation identified are similar, they have the same speed. They have the same speed. They travel in a vacuum. They are electromagnetic. They are transverse. They are all the same. Okay, the same speed. One way in which light is different from infrared radiation, light has a higher frequency. Light has a shorter wavelength. Light, okay, you can say that light has a higher frequency, or you can say it has a shorter wavelength. These are all some questions Again, another question. I'm sorry, I said the last question, so I meant to actually solve this question. It's very easy. Let's solve it together. Three components of the spectrum, J, K, and L. Name these components, gamma rays, and I know them. I can just write down Rami looks great. So L is radio waves. L is radio waves. Microwaves, and then infrared. Okay, infrared, then visible light, and this is the ultraviolet. صح? Ultraviolet. State which of these three components has the lowest frequency of these three components. The radio waves. صح? Radio. Calculate the frequency of X-rays that has a wavelength of 1.9 times 10 to the power of negative 9. Actually, in your exam, he could write it down as 1.2 nm. N is nano, which is times 10 to the negative 9. N is small n is a nano, which is times 10 to the negative 9. Can I find the frequency? Yes, definitely. Frequency is speed over wavelength. Speed is 3 times 10 to the power of 8. 1.2 times 10 to the negative 9. It would be a huge number. Okay, it would be around 2.5 times 10 to the power of 17. Oh, 3 over to the power of 17 hertz. Do not forget the unit. Describe one medical use of X-rays. Scanning broken bones. It's not worth 3 marks. It's not worth 3 marks. Scanning broken bones. What do I do? I know why. Okay, they can pass. Oh, they can pass through human flesh and bones. Okay, they can pass through human flesh and bones, but as they pass through different densities, an image is produced because the density of the flesh is different than the density of the bones. So as they pass through flesh and bones, the densities differ, and therefore an image of this bone is produced. In scanning, okay, broken bones, we can say as X-rays pass through broken bones, through flesh and bones. Okay, flesh and bones. Densities are different. Yeah, densities are different, and an image is produced. And an image is produced. Okay. Okay. One reason why is it necessary to take a safety precaution to take safety precautions while when X-rays are used. X-rays are very harmful. X-rays can cause what? What can they do to human cells? They can cause mutations. They can kill healthy cells. They can cause cancer. Excessive use of X-rays can cause cancer. Yes. Okay. So they can cause mutation or cancer. Okay, they can kill healthy cells. Okay. Okay, good.